Welcome, ladies and gentlemen, to this video lecture. Okay, so now we will be starting chapter 4, which is integration and application. Okay, let us talk about this chapter. So the main, or let's say one of the main themes of this chapter is what is called the fundamental theorem of calculus. Fundamental theorem of calculus. Okay, and this theorem makes rigorous the relationship between the derivative and the integral. So you've already been getting used to this relationship, meaning, or what is this relationship? The integral is just the reverse of the derivative. So these two operations are inverses of each other. And the fundamental theorem of calculus will make rigorous what we mean by that. And this we will see later. So for the moment, what we will be looking at is consequences of the fundamental theorem of calculus and how these consequences are of use in computing integrals, in developing techniques in how to compute integrals. So the first technique that we will learn is what is called integration by parts. Integration by parts. Okay, and what is integration by parts? So integration by parts is an application of the fundamental theorem of calculus and the product rule for derivatives. So let's write down exactly what we mean by this. So let f and g be functions defined on a closed interval from a to b, and let these functions be differentiable. So these functions are differentiable on this closed interval AB. And with continuous derivatives. So the derivatives are continuous. Continuous on the interval AB. Then the following holds. So the integral of the product of f of x, g of x, dx, actually the derivative of g of x. So the integral of f of x times g prime of x, this is equal to the product of f of x and g of x evaluated on the endpoints from a to b. So you should have seen this notation already when computing integrals, minus the integral from a to b of f prime of x, g of x, dx. Okay, so let us take a look at what is going on here. So we see here, if we want to compute an integral of the product of two functions, where one of the functions is a derivative, then we can move the derivative to the other function. Notice that here we can change the derivative from the one function to the other function, to get the following here, and we have to add this term over there. So that is the idea. So the whole point here is to, if we are confronted with an integral of this form that we cannot do, we can transform this integral by moving this derivative to the other function and keeping in mind how to do that. And hopefully that will make computing our integral a little bit easier. Okay, but before we look at an example, let's just think about where the hell this equation comes from. So what is this? This is, and you will see now, this is the product rule combined with the fundamental theorem of calculus. So let us prove this formula. So proof for all x in our interval AB, if we look at the derivative of f times g at x, now we just apply the product rule for derivatives. That is derivative of f times g plus f times derivative of g. Okay, and now we apply the fundamental theorem of calculus on both sides, or we apply the fundamental theorem of calculus, and the fundamental theorem of calculus says the derivative is the inverse operation to the integral. So we take the integral from a to b on both sides. Actually, before I do that, let's write down what we are doing. Take the integral over AB on both sides. Then by the fundamental theorem of calculus, we get the following. So if we take the integral now on both sides, so we take the integral from a to b of this derivative. On the other side, what do we get? We get the integral from a to b of f prime x gx. Let's move this a little bit over. Plus the integral from a to b of f of x g prime of x dx. I need a bit more space. Meh. Dx. Okay, and now by the fundamental theorem of calculus, this term, we're taking the integral of the derivative by the fundamental theorem of calculus. This then just becomes f of x times g of x evaluated at the endpoints, like so. And this is then equal to these two integrals, or the sum of these two integrals from a to b, f prime f of x g of x dx plus the integral from a to b f of x g prime of x dx. And now we see here, if we slightly rearrange, we get exactly the formula that we had earlier. So if we take, let's reflect this this equation and just take this to the other side. So I'm going to start with that term, the integral from a to b of f of x g prime of x dx. This is equal to, and now what are we doing? We're taking that term across. This is equal to f of x g of x evaluated at the endpoints from b to a minus the integral from a to b of f prime of x g of x dx. Okay, so here we see that the technique called integration by parts, all that this is the product rule for derivatives combined with the fundamental theorem of calculus and some rearrangement of the formula. So you don't always, or you don't really need to remember this formula. If you remember exactly where it comes from the product rule and the fundamental theorem of calculus, you can always reconstruct it if you forget. However, it would be a good idea in this course to actually remember it, but in the far future, if you ever have to apply integration by parts, and you forgot how to do it and you don't have internet access to look it up, then remember you can always reconstruct it by just applying the fundamental theorem of calculus and the product rule for derivatives. Okay, so in the next one we will take a look at an example. I will see you in the next one.